Another common use for the t-test or of the t-test for a population mean is in before and after situations, quote unquote. In this situation, we have two quantitative measurements from a single sample of individuals. It's kind of hard to wrap our mind around, but so here's an example of a matched pair design, they call it. So here's an example about drinking and driving. Okay. We have a nice table down here. It says that the Centers for Disease Control and Prevention, the CDC, website cites studies from the National Highway Traffic Safety Administration to support this statement. Quote, alcohol use slows reaction time and impairs judgment and coordination, which are all skills needed to drive a car safely. The more alcohol consumed, the greater the impairment, unquote. All states in the US have adopted a blood alcohol concentration of 0.08% or 80 milligrams per, I don't even know what that is, DL? Decaliter? I don't know, as a legal limit for operating a motor vehicle. The CDC website continues, quote, note, legal limits do not define a level below which it is safe to operate a vehicle or engage in some other activity. Impairment due to alcohol use begins to occur at levels well below the legal limit. So they're saying even if you somehow take a breathalyzer test and your alcohol concentration is less than 0.08, that doesn't mean, okay, you're good to drive, go. They're saying that's like where you could get in big trouble. But below that, you should still be careful if you're drinking. It is this last statement that may be surprising to drivers. Interviews with drunk drivers who were involved in accidents reveal that drunk drivers do not realize how drunk they are. Quote, I only had 1 or 2 drinks. I'm okay to drive, quote unquote, is a common sentiment. Suppose a college conducts a study to call attention to this issue. Researchers use a random sample of 20 college students to examine the effects of drinking 2 beers on reaction time. They use a driving simulator to measure each student's reaction. So they're not really making these drunk kids drive, okay? They're just a simulation, so they can't get hurt. They measure each student's reaction time before and after drinking 2 beers. The reaction time is the time it takes the student to hit the brakes in the simulator when an obstacle appears in the road. So here's the data below. Let's look down at that table. Reaction times of students. So there are 20 different drivers. You see that in the first column. The second column has their reaction time. So it's quite a range. It goes from kind of as high as it takes someone more than 6 seconds to react, and then as low as maybe a little less than 4. So it's somewhere between about 3.5 seconds and 6.5 seconds to react. But after, notice that everybody's time goes up. It goes higher after you drink 2 beers. And then it shows here the last column is probably the most interesting. It's the difference between them. This person, it takes an extra 60 seconds for them to react after they've had 2 beers. This one, it takes them an extra, or sorry, not 60 seconds, 0.6 seconds. The second one's an extra 1.82 seconds, which doesn't sound like a lot, but if there's an obstacle coming at you in the road, that's actually quite a bit, and you might not have enough time to react, and you might hit it or swerve and hurt yourself. Some of them aren't so bad, right? Like 0.07 seconds, that's not really a lot. But of course, all this also depends on your body weight. Alcohol affects people that don't weigh as much, and yeah, right. So that's probably what you see as the disparity here. Some people, though, you noticed actually got better. What the heck? This person, before they had 2 beers, it took them 5 seconds to react, and after it took them 4 seconds to react. Okay, so that might be just random chance, but interesting. Okay, now let's look at the analysis here. In this situation, we have 2 quantitative measurements for each student. To measure the effect of the 2 beers, we subtract the 2 reaction times to create one measurement of change or effect. So like we saw, it took 0.06 more seconds to react when they had 2 beers or whatever the number was. This controls the effect of individual characteristics that could influence reaction time, such as driving experience or natural quickness. We define the difference as before minus after. A negative difference in the last column means that the person has slower or longer reaction time after 2 beers. Positive difference in the last column means that the person had a faster or shorter reaction time after 2 beers. Note, it is common to define the difference in measurements as before minus after, but we could also define the difference the other way around for after minus before. In this definition, if the after reaction time is longer, then the difference is positive, so a slower reaction time after drinking corresponds to a positive value. This makes less intuitive sense to us. We want negative to mean drinking has a negative effect. So that's why we did it that way instead of switching them. So we use the other definition, before minus after. Like I said, because that'll produce a negative effect for people that get worse with beer in their driving, and then a positive effect for those that get better somehow. Step 1, determine the hypotheses. First, the null hypothesis is the claim of no change or no effect. The alternative hypothesis, remember, is it reflects some kind of change. So here I'll say the null hypothesis is that drinking 2 beers has no effect on reaction time. Some people think that, and maybe it's true for some people. The alternative hypothesis is that drinking 2 beers slows reaction time. If drinking 2 beers has no effect on reaction time, remember we just assumed the null hypothesis is true. So right now I'm assuming that 2 beers has no effect on reaction time, and then we'll see if some data refutes that and says I was wrong when I said the null hypothesis, or there's no data that can refute it. Then the mean of the differences in reaction times before minus after will be 0. If drinking 2 beers slows reaction time, then the mean of the differences in reaction times before minus after will be negative. So in other words, if I take that last column, let's see, that last column in there, if I take all these values, that's the before minus the after, and I find their average, it should be 0 or a positive number. If it was 0, that would mean that there's no change in the before reaction time versus after 2 beers. If it's positive, that means that people on average actually got better at driving, which is kind of not intuitive, right? But if I get a negative number, depending on how large of a negative number or how far from 0 it is, I guess that could possibly mean that I was wrong with my null hypothesis. Okay, that's the idea. So in other words, in symbols, it means that our null hypothesis is that mu is 0. Before minus after is going to be 0. Like we said, before minus after, if 2 beers doesn't affect anything, then my reaction time won't change. My reaction time before I have 2 beers and my reaction time after will be nothing. They'll be the exact same thing. So if I subtract them, I should get 0 on average with all the people. But we're kind of thinking, well, I think our reaction time is going to change. It's going to be less than 0. It'll probably be negative, because remember, a negative before minus after means that your reaction time was hindered by the 2 beers, where mu is the mean of the difference in reaction time before minus after for all students at this college after drinking 2 beers. Suppose that researchers set a significance level of 5%. So we've said before in previous pages in this module that the alpha or the significance level should be given to you. So you kind of know where the cutoff is. When do I believe the null hypothesis? At what point do I stop believing it? Kind of. Note, if we define the difference in reverse order as after minus before, then a positive difference corresponds to a slower reaction time. This changes the alternative hypothesis to be the opposite. I would want mu to be greater than 0, not less than. But we've defined it as before minus after, not after minus before. This will not affect the p-value of our conclusion. So you just have to make sure the alternative hypothesis says what you want to say, given the way you define the difference. Note, in some textbooks and other statistical materials, you will see the mean difference written as mu sub d. The mean difference. The definition of difference in math is subtraction. So if you're subtracting 2 things and you want to find the mean or the average of all those things you're subtracting, you call it mu sub d, or the mean of the difference. Just in case you ever see that, now you know what it means. Step 2, now that we've stated the hypotheses, we'll collect the data. Now we use the data from our supposed sample of 20 college students to calculate the mean and standard deviation of the differences. Again, there are formulas to calculate these, but in this class, we're not worried about it. We'll use Applets or StatCrunch or whatever it is to calculate the mean and the standard deviation. So the mean of the differences before minus after, if I take all the values in that very rightmost column of that table above, you get negative 0.486 seconds. And that's just, you add them all together, all 20 of those values in the rightmost column, and you divide by 20 the number of values. That's what you get. The standard deviation, which is a more complicated formula, and we're not worried about it in this class. That's, for a different, further off statistics class, if you ever have to take it, is approximately 0.87 seconds. So step 3, now we're going to assess the evidence. Okay. Check the criteria for the use of a t-model. Based on our numbers and the samples we took, can we use a t-model? Well, the sample size is only 20, so we do not know if the differences would be normally distributed in general when comparing these 2 treatments in the population of a college student. We therefore do not meet the conditions for use of a t-model. Some researchers would stop here and not complete the hypothesis test. Others would check the shape of the distribution of differences in the sample. If the sample is approximately normal, or at least not heavily skewed right or left, then they view this as a hopeful indication that the distribution in the population will also be approximately normal. And they continue with the hypothesis test, adding a disclaimer to the conclusion. There was a histogram of the differences in the sample. So this looks approximately normal, right? There's a peak in the middle. It kind of tapers off to the ends. The data is definitely not skewed. So we're willing to proceed with the t-test. I don't see any outliers, right? We add a cautionary note in our conclusion. So just make sure in your conclusion, let's just make sure that we have our cautionary note. Okay, we don't know really if this is normally distributed, and we might not have 30 or more people in our sample, but this is what we got. So let's compute the test statistic. Okay. Within calculating the test statistic, we have to calculate the standard error. So we might as well do that first. The sample standard deviation over the square root of the number of people we sampled. It was the standard deviation we saw earlier was 0.87. They told us over the square root of the sample size is 20. There were 20 college students. If you take 0.87 and divide it by the square root of 20, you get about 0.195. So the test statistic, or the t-score is the statistic, the value that we got, the mean, mu d, I think we called it, right? The mean difference minus the mu that they think in the null hypothesis is the case. They said supposedly the difference is going to be 0, that there's no change after I drink 2 beers, divided by the estimated standard error, and we just calculated that to be the new denominator 0.195. That was the calculation above. Oops, shoot. Here. And then if you divide those, negative 0.46 divided by 0.195, it's about negative 2.36. Negative 2.36. Okay. So we found the t-value. Now we'll use the applet with the t-model for 19 degrees of freedom, because remember, degrees of freedom is n minus 1, and in this case, n is 20. So 20 minus 1 is 19 degrees of freedom. And the p-value that we got would be, if we put in the t-value that we calculated up here, and then the degrees of freedom being 19, the p-value is about, it's here, 0.0146. If I round that, it's about 0.015 if I round it, or you can keep it as 0.014. Okay, so what does that tell us? Now that we know the p-value, let's state a conclusion. The p-value that we got when we used the applet, 0.015, is less than the significance level alpha that we were given in the beginning. They said alpha is 5%. In other words, in decimal form, 0.05. So we reject the null hypothesis and accept the alternative hypothesis that mu is less than 0. This study suggests that reaction times when driving are significantly slower when drinking 2 beers for students at this college with P. And then if you state this conclusion in some kind of an article or whatever it is, you'd probably say what P is equal to, just because there are people that are reading that might understand statistics and might be interested in the details. It's good practice to include a disclaimer with this conclusion, because the sample is small. So we might add the following to our conclusion if we were publicly representing these claims. And quote unquote, the sample was too small to formally meet the requirement for a t-test. On the basis of this data, we are assuming that the difference in reaction times would be normally distributed in general. When comparing these 2 treatments and the population of all college students, the conclusion from this test is valid only if this assumption is true. So this is our conclusion, and we're pretty sure we're right, but we could be wrong. Okay, chances are not very good, but it's possible. Okay, now a comment. From this study, can we generalize to a larger population of quote unquote all college students or all drivers? Technically, such a generalization requires that the sample be randomly selected from the more general population. These are teenagers, they're all the same age group, so maybe they behave differently. Maybe they're more susceptible to beer or less than adults, that are older, who knows? Is this type of random sampling done in practice? Well, not always. The matched pairs design controls for individual differences that would otherwise confound such a generalization. This is one of the reasons that researchers run hypothesis tests with data gathered by groups like the National Highway Traffic Safety Administration, even when participants are not randomly selected. But ideally, we should select samples randomly from the population of interest to get a true sense of the data for the overall population. Another question might be, can we make a cause and effect conclusion from the study? We should be cautious about cause and effect conclusions because there is no random assignment. We take measurements from every student in both the treatment and the control setting without randomizing the treatment order. Every participant did the driving test sober, then drank 2 beers and did the driving test again. Technically, we need a more sophisticated study design that uses random assignment in order to make cause and effect conclusions. So for example, we could randomly assign the treatment order for each student by flipping a coin, assigning some students to do the driving test while sober and others to do the driving test after drinking 2 beers. Then everyone comes back another day to complete the part of the experiment that he or she had not done. So if you had done the first part after drinking beers, you would come back a couple days later sober and take the test. If you had taken the test sober initially, you'd come back, drink a couple beers, and then take the test. The next activities we do give you an opportunity to practice parts of the hypothesis testing process. In each of these activities, the study is matched pair design, so the population mean represents a mean of differences in paired measurements. Later, you will have the opportunity to practice the hypothesis test from start to finish.